Welcome to Math 109 online lecture, Introduction to Algebra. In this course, we're going to talk about sign number rules, look at some algebraic expressions and how to combine like terms, and use all of this information to solve equations and formulas. And why do we care about this in Math 109? Well, many of the things that we've worked with in this class, like when we solve for dosage calculations or determine BMI or resting heart rate, these all come from formulas. Even our Fahrenheit to Celsius and Celsius to Fahrenheit equations are formulas themselves. We want to be able to work with them and rearrange them to solve for variables that we're looking for to make them work as efficiently as possible. So in this online video, what we're going to do is cover concepts, and there'll be practice problems that you can try. Now, what I suggest is that depending on your skill level, basically how much knowledge you have of algebra, will really depend on what you need to spend more time with and what you might be able to move through a little bit more quickly. So along with this online lecture video, you are working through the Solving Algebra homework worksheet, and that will reiterate the concepts that we cover. If you find you don't need to watch the entire video, that's fine. Watch what really is impactful for you. If you find that you need to do some more work outside of the online video, please do stop by during my office hours, which are on your syllabus, or stop by the math lab, as they can be very helpful in this area, among others. All right, so let's get started. One more thing to note here, as we move along, you can pause at any time so that you can watch specific parts. You can pause the video so that you can try the practice problem, as they will be worked out throughout this entire online series. Okay, here we go. So the first thing we're going to talk about are sign numbers. And when we talk about sign numbers, we basically have different rules for addition, multiplication, and division. And when it comes to addition rules, when we're working with same signs, regardless of what the absolute value is, what we find is that if we've got two numbers that are opposites, like 3 and -3, when we take their absolute value, which looks like this, they're going to be equal. And that's because absolute value represents the distance from a number and 0 on the number line, which just basically means the magnitude of the number. So when we work with same signs, if they have the same sign, not only are their absolute values the same, but also, or excuse me, if they have the same sign, I should say their absolute values aren't necessarily the same, but they will be on the same side of the number line, so they're working with each other. Notice if we have same sign here, regardless of whether we're talking about negative or positive, we're either on the eastern or the western side of the number line. So if you notice here, if you add +3 plus 2, you get 5. And if you add -3 plus -2, you get -5. That's how many units we'd have to move away from 0 in the negative x direction on the number line in order to get to our final result when we add these two quantities. So with that said, notice that the only thing that's really different here with same signs, regardless of whether the signs are positive or negative, the resultant answer here, our sum, has the same absolute value. The only thing different is the sign. So when we add two negatives, we result in a negative sum. When we add two positives, we result in a positive sum. So the way we can say this more efficiently is when we're dealing with same signs, we're going to add the absolute values together and keep the sign that we're working with. However, when we work with different signs, things are a little bit different here. And the reason for that is because when we're working with different signs, and we think about the number line, excuse my lack of ability to draw a nice straight line here, here's our 0. Positive values in this direction and negative values in this direction. If we look at -5 plus 2, let's say that -5 is somewhere over here, 5 units to the left of 0. If we add only 2 units to that, we land ourselves at -3. And that's because the magnitude of 2 isn't large enough to pass 0 on the number line. So notice that these two work against each other. -5 is moving west or towards the negative direction, while +2 is moving east. And what happens? is we end up in a location west of 0 because we haven't crossed 0 on the number line. So with that said, basically what happens here is the big guy wins. And what I mean by that is, if you notice, these two are working against each other. -5 plus 2. If we think about that, 5 minus 2 equals 3. The reason we're negative in this case, the difference is negative, is because the 5 is negative and the magnitude of 5 is a lot bigger than the magnitude of 2. So what happens here is when we're dealing with different signs, what we're going to do is subtract the absolute values and keep the sign of the larger number. Because here the larger number will win and keep us on that side of the number line. So when we look at the next example, 12 plus -3, if we think about subtraction, 12 minus 3 is 9. And the reason that it stays positive is because 12 is positive and much larger than 3. So we can generalize these rules, and here let me just clean up my mess here, to state that when we're dealing with same signs, what we're going to do is add the absolute values, the magnitudes of the number, and keep the sign we're working with. If they are different signs and they are working against each other because of the different signs, what we're going to do is subtract the absolute values, always subtracting the smaller from the larger, and keep the sign of the larger number. So if your larger number is negative, then your answer will be negative. If your larger number is positive, your resulting sum will be a positive value. All right, let's move on. So where do you find your negative sign on your calculator? Notice what you want to stay away from is your subtraction key. Here I've picked a Casio and a TI, which is a good representation of most of the calculators that people have in class. So if we look for our negative key on the Casio, notice it's right here. This is how we indicate a negative number. On the Texas Instruments calculator, you'll notice that your negative is to the bottom right. So that's how you can indicate a negative number on that calculator. While we're going to discuss the rule of signs as they apply to different operations, what I want you to remember is that your strongest tool here is this right here. When we get to algebraic applications, we don't want to be hung up on making arithmetic mistakes like sign errors. So in order to avoid those, what we'll do is make sure that we validate our results in the calculator. But before we get there, let's just understand the concept of these sign numbers so that we can trust our results and make sure that we import things correctly in the calculator. All right, let me just clean this up here in case we come back to this slide. So now subtraction is a little bit more rigorous than addition, because if you look below, look at all the different examples we can run into, all the different cases. So since subtraction can be a little bit more rigorous, and we've seen this with keep, switch, and flip, this is kind of the same idea, what we can do is we can take any subtraction problem and rewrite it as adding the opposite, since they mean the same thing. So if we look at this first example, we have 5 minus -2. If we go ahead and look at how we can rewrite this, this becomes 5 plus, we're rewriting our sign as addition, and since we subtracted a -2, we'll add a +2. Notice that subtracting a negative is kind of sneaky. It's really the same thing as just adding a positive. And that's how we get a resulting sum of 7 here. So now we can take any number, and let's just look at one. Say we have -18 minus -7. If we rewrite as, adding the opposite, notice what we're really doing is keep, switch, and then instead of flip, change. Keep, switch, and change. We subtracted a negative, so we're adding a positive. So what we have here now is -18 plus 7. And I'll clean that up a little bit. Now this should look familiar, because now all we simply have to do is use our addition rules to solve it. Since it's different signs, 18 minus 7 is 11. And since the larger number is negative, our resulting answer will be negative as well. All right, moving on. So next comes our multiplication and division rules. And I've always liked having a good little phrase here that I think many students can agree with. And that's, in this case, math is definitely evil. Two wrongs make a right. Anytime we multiply two negatives together, we result in a positive answer. Math is also evil because the bad guy always wins. Anytime we have negative times positive, it results in a negative result. So what this means is if we have an odd number of negative values being multiplied together, the resultant product is also going to be negative. If we have an even number of values multiplied together, that resulting product will become positive because negative times negative equals positive. What's nice about this rule, a little different than addition and subtraction, is that here, notice whether we're talking about multiplication or division, we're talking about the same darn thing. Since we don't really change our sign when it comes from multiplication and division, think about it. 4 divided by 2 is the same thing as 4 times 1/2. They share common properties, so do their signs. So something we always know, positive divided by positive is positive. Negative divided by negative will yield a positive result. And negative divided by positive or positive divided by negative will yield a negative answer. So now that we know these rules, let's apply them and let's use the calculators to validate our results. So if you want to pause the video here, you can, and take a moment to work through these examples. All right, so let's look at what you should have gotten for examples, and you should have validated these results on your calculator. We look at example 1, notice we're subtracting a negative. That's the same thing as adding a positive. Different signs means keep the sign of the larger. So what we have here is 8 minus 7 is 1, and it should stay positive since our largest value is positive. If you put this value in the calculator, notice 5 plus negative 14 gives us negative 9, and now we have minus 36. You can rewrite this as negative 9 plus negative 36, but if there are no parentheses in a subtraction problem like this, you can really cheat a little bit and sneak in a little plus here anyway. Notice, really, anytime we have a subtraction problem that looks like this, when we're just subtracting a number, we're really adding the opposite. All we're really doing is looking to see whether we have same signs or different signs and going right to our add rules. Since they're the same sign, 9 plus 36 is 45, and we're going to keep that sign that we worked with. So our final answer here would be negative 45. In the calculator here, when you work out this one thing to know is that in order to be mathematically, grammatically correct, we don't like to have negatives inside the denominator. So since we can't cancel out that negative, I'm just going to put it outside of this fraction. And since both of these guys have a common factor of 3, let's divide it out of top and bottom. If you left your answer here as an estimated decimal, that's great. That works just fine here as well. In fact, that relates back to more of a measurable quantity. Now here we have negative times negative, which gives us a positive result. And when you multiply these values together, you get 12.375. All right, I think we're ready to move on. This next example is a little bit more work because here, and we talked about this in our order of operations, here it's really important to validate the difference between using a set of parentheses or not. Notice here we have negative 2 raised to the 5th power. Now, let's just go back here for a second, and let's just remember where that exponent key is on your calculators. Notice it's that up arrow key, and in this case, it's the up arrow key on both of these calculators. Some keys have a y to the x key, and that would be your exponent key. So to put something in like this, we want to use our parentheses and open up that set of parentheses, put in our negative 2, close those parentheses, and then use our caret key or our exponent key to raise to the power of 5, and then hit enter. All right, so if you take -2 to the power of 5, you should yield a result of -32. And that makes sense since it's -2 multiplied to itself 5 times. Now, why is your resultant answer negative? That's simply because we have an odd number of values that we multiplied together. Let me make sure that looks negative. Now, how about -3 to the 4th power? This should give you a positive 81, and that is because we are taking the base -3 and multiplying it to itself 4 times. Notice, even number of negative values being multiplied together gives us a positive result. Notice -2 to the 5th gives us -32 as well. Here's something interesting about this one. This is really saying take the opposite of 2 to the 5th. Since in this case there are no parentheses, the only thing that's being raised to the 5th is the base of 2. That negative is indicating the fact that we're going to take the opposite of that answer. So here, this is really the same thing as saying -1 times 32. So if we go back and we look at -3 to the 4th power, what would you expect to get, excuse me guys, what would you expect to get as an answer? Just clean this one up to give a little bit more space. Well, here what it's really saying is let's take the opposite. I like to say -1 times 3 to the 4th power, which is 81. Remember, order of operations, we're going to apply the exponent before we multiply by -1. So what does this do? It results in a negative product. So now try the next one in your calculator. What you should receive is -2, since -2 to the 5th gives us -32. And using your set of parentheses here, now you can see the importance of not using them and using them. It's the difference in sign of your value. -4 squared gives you a positive 16. Negative divided by positive leaves us with an answer of -2. If we work out the next example right in the calculator, what you should receive as a result is -0.0336. So you can try that one if you like. I'm just going to clean that up a little bit right there. Sorry guys, just trying to get my pen to work properly here. There we go. There we go. Sorry for the momentary lapse there. Clearly that negative did not want to go away. All right, so we are ready to continue to move on. You can see how easy it is to make a potential sign error and why it really is critical to use your calculator during these applications. All right, so now let's get into the thick of it and let's start using algebra. And the first rule that we're going to start with is the distributive property. And the distributive property basically says anytime you have an outside factor being multiplied to some sum of numbers inside the parentheses, you're going to multiply that outside factor to each term inside those parentheses. And when we talk about terms, terms are the values that are basically made up by coefficients or constants and variables. 2x is an example of a term. -10a is an example of a term. Even 40 is an example of a term, but we tend to call that a constant. So if you look at this example that we have here, I will get this pen to work here. Bear with me one second. Come on, little pen. Gotta love technology. There we go. If we get this pen to work, I want to show you guys something here. So if we look at this example, notice 2 times -3 gives us -6. So that's the first piece. Then we have 2 times +7, which in this case is 14. Whether you use order of operations and do the work inside the parentheses first to give you 4 and then multiply by your outside factor, you end up with 8. If we use the distributive property in this case and we work with what we've got right here, notice that -6 plus 14 also gives us 8. So it's true to see just with looking at just constant numbers that this distributive property works. Now, there's a few different ways to go about this process, and this is what I want you guys to be really, really comfortable with. If we look at this example, notice what we have here is 5 times 2x minus 8. So we multiply the first terms together, 5 times 2x. Then we multiply the second terms together, and you can see they're separated by addition, 5 times -8. What that gives us is 10x plus -40. Notice the result is written as 10x minus 40, and that's because we know that adding a negative is the same thing as subtracting a positive. I'm a little bit more lazy in my approach, and you might like this, so I'm going to show you. I tend to go like this, and tell me what you think. I look at them as signs. So I always think sign, then number, then letter. That's how we handle algebraic operations. First off, 5 times 2x, they're both positive. So I know my answer will be positive. Now the numbers, 5 times 2 is 10. And since we just have x, there's no other variable to multiply to, that x just comes along for the ride. Now if we look at the next two terms, if we look at 5 and -8, positive times negative, that gives us a negative value. There's the sign in that SNL. 5 times 8 is 40. And since there's no variables, we're done. All right, let's do a few examples together. And if you want to pause the video, you can, and you can try these examples on your own and then start up the video to see how you did. Okay, so let's take a look at these together. So if we look at the first one, negative times positive, that gives us -21, and we just have an x coming along for the ride. -7 times 4, well, that's negative times positive, so minus. 7 times 4 is 28. Notice something. There were two terms that started inside that parentheses. We are ending with a two-term expression. They're not like terms and couldn't be combined here. So they're not going to be able to be combined once we simplify this by the distributive property. Now remember, anytime we take a number and we multiply it to itself, it's that value squared. So when we look at this example here, 3x times 4x, well 3 times 4 is 12. X times x, we write that as x squared. And then positive here times negative gives us a minus. Now the numbers, 3 times 3 is 9, and we're left with an x here. Nice. All right, now what happens here when we have a negative outside of the parentheses? Notice that when we're taking the opposite, it's the same thing as just multiplying by -1. So -1 times 3y is -3y. And negative times negative, -1 times -5 is a +5. The only thing that changes here is magnitude, not sign. Now the last one we want to be real careful with because we have two variables in this outside term, 3xy. So let's start with 3 times 5, that's 15. X times x is x squared, and it's like we have times y times 1. It's got nobody to multiply to, so it just comes along for the ride. Now positive times negative, 3 times negative 2 is going to be a minus 6. We have x times x, that's x squared. And we also have y times y, so that's y squared. When you look at 3xy, oops, excuse me guys, got a finicky stylus. When you look at 3xy and you compare that to 2xy, one thing that you can do to make your life a little easier in this problem is actually rearrange your pieces if this is new for you and you're trying to understand it. Notice that we can put the numbers together and we can put the variables together. I just rearranged this and we're able to do that since multiplication is commutative. Here you can see your 6, x times x is x squared, and y times y is y squared. All right, moving on. The last thing that we're going to talk about is combining like terms before we start to solve some algebraic equations. So when we're combining like terms, what I want you to remember is this is different than multiplication or division. If we look back here, notice when we multiply, like for instance, x times x, we get x squared. But when we combine like terms, we look for variable terms that have the same variables and their variables have the same exponents. That way they are sharing that in common, and that commonality we know is like terms. Now, with that said, when we add like terms, the only thing we're really doing is combining their coefficients. Negative 17 plus 3 is negative 14. Notice that our exponent didn't change. It's still x to the 5th. And doesn't that make sense? If you're adding like terms in real life, like you buy, let's say you've got an unlimited bank account, you buy 6 pairs of new sneakers, and then you go out and buy two new pairs of sneakers, you have 8 pairs of sneakers. You don't suddenly have 8 pairs of sneakers squared. So this is going to work the same way. We look for like terms. Like terms are the terms that contain the same variables, and those variables contain the same exponents. When we find like terms, we combine them through addition. We do not change their exponent values. Excuse me. So if you'd like to take a moment and try example 4, please do. And we will get going on this in just a second. All right, so let's take a look at this together. Look at our like terms for number 6. Whoops, excuse me. We only have 2, 5x and negative 7x. So 5 minus 7 is negative 2. This is where you should really be using your calculators. And we're going to bring that x along. Now 2y comes along for the ride. It just doesn't get combined with anyone. And then lastly, we have this constant of 12. Now let's look for like terms in number 8. Excuse me, no number 7, I took it out of there. So what we have is 2x squared y and negative 5x squared y. So 2 minus 5 is negative 3x squared y. And now let's go for the next like term. We also have 4 and 6xy squared. 4 plus 6 is 10. Xy squared. So that's what we have. Whoops. Now, lastly, we have a negative 3xy and a positive 6xy. Negative 3 plus 6 is a positive 3, so we're adding 3xy. Notice something about this remaining expression. These 3 terms can't be combined because they're not like terms. This is about as good as it's going to get. All right, now, next step here, we're going to take a look at number 9. And in number 9, notice that we're going to start bringing everything together. We can't combine these like terms because we have parentheses. So the first thing we have to do is distribute these like terms distribute these terms so that we can combine them. I like to call this having to be free to roam about the cabin. We don't know what we can combine until we know what we have left. So negative 3 times 2x, that's negative 6x. Negative times negative, 3 times 4 gives us a positive 12. And then we're adding 2. So notice the only like terms we have in this example are our constant terms, 12 plus 2. So I'm going to bring that negative 6. And then plus 12 plus 2 is plus 14. And there's our resulting expression. Now we've got 2 terms to distribute in number 10. And what we get here is 4x plus 12 plus 10x minus 30. And this is what's going to look very familiar to us in the next part of this online lecture, because we're going to be solving equations containing one variable with only one exponent here, basically an exponent of 1. So we'll combine like terms before we actually solve for that unknown value. So here we've got 4x plus 10x, which is 14x. And we also have 12 minus 30, which is going to give us a negative 18. All right, so there it is, 14x minus 18. Not too bad. And all we've done so far is just really build upon everything we've looked at. Now, as we migrate to solving equations, I can't stress it enough. It's so important that you use your calculators to check your values, because the biggest error students make is sign errors. And it's natural, because when your brain is focused on algebraic concepts, it's really hard to focus on arithmetic at the same time. We're humans, even supercomputers cannot really process functions at the same time. They just do it really fast. So it seems like they do. They're not that smart. All right, so here we go. Let's go ahead and start solving equations. And this is where we're going to take everything we've discussed and put it all together. When we're solving equations, we're basically trying to isolate a variable and get it by itself on one side of the equation. And we have different types of basically tools that we can use to solve equations. And we have what's known as the addition and multiplication principle. So let's start with the addition principle. And when you think about equations, you can really think about them like a balance. And the only way that balance is going to stay level is if our two sides of the equation are equal. So the question is, what value for x continues to keep this balance level, or keep these two equations being, two sides of the equations being equal? Well, here, just by looking at it, we can see that it's 28. 28 plus 7 is 35. So now what we do is, with the addition principle, what our focus is, let me just clean this up, guys, is to look at what's being done. If a number is added to one side of the equation, we can subtract that number from both sides of the equation and continue to maintain an equal statement. And that can allow us to get that variable solved and isolated by itself. So notice in this case, since 7 is added, we can subtract a 7, which is the same thing as adding a negative 7 to both sides. Night, night, there goes our plus 7. It really moves to the right-hand side of the equation. So now, like you can see here, x plus 7 minus 7, these guys cancel. That's the whole point of doing that. It brings it over to the other side. 35 minus 7 is 28. And one thing that's beautiful about stuff like this is that it's so easy to check your work. Just substitute your value that you solved for back into the original equation. Here we can just do a mental check. Yes, 28 plus 7 does indeed give us 35. So now let's look at example 2. Well, one thing that I want you to keep in mind is when you have examples that have like terms on either or each side of the equation, what a really good idea to do is to actually combine your like terms first and then use the addition or multiplication principles to solve. So notice here, 5 minus 19 is negative 14. So this really says the same thing as x minus 14 equals 90. And I've always looked at Algebra is like playing a game. And yes, you may think it's a sick and twisted game, but a game nonetheless. And I say that because I always think about almost like playing chess. What's being done to my x? That's on this side of the equation. Well, 14 is being subtracted from it. What undoes that? Adding 14 to both sides. So here, if we undo what's being done to the variable, we can solve for it, leaving us with x equals, oh, excuse me, my apologies. This is not a 60. Let me make sure that I've got the right value expressed here. And let me make sure that my eraser function wants to work properly, and it does. Okay, good. So 60 plus 14 gives us 74. And if we test it, 5 plus 74 is 79, minus 19 equals 60. Always go back and check your answer by substituting into the original equation. The reason is let's say we had made a mistake like I just did. We might not catch it with the new variation of the equation we created, but we will catch it with the original every time. All right, now we have another principle. We have the multiplication principle. And the multiplication principle pretty much states the same idea. If you've got a number multiplied to your variable, notice 3x means the same thing as 3 times x. We assume there to be this between them. Then you can undo it by dividing by that number on both sides of the equation. Whatever you do to one side, as long as you do it to the other, just like fractions, you'll maintain equality. So since 3 is being multiplied, I'm going to divide both sides by 3, leaving us with x equals 5. And if we have a number that is multiplied here, notice negative 2/3, we can divide both sides by negative 2/3. Since that's the number that's being multiplied, notice we take the sign along with it. That's the number we're going to divide by. But putting this in the calculator can be tough. So we have a bit of a shortcut here that helps make life a lot easier. And that shortcut is, since we know dividing by a fraction is the same thing as multiplying by the reciprocal, we can go right to it. The reciprocal of negative 2/3 is negative 3/2. So I'm going to multiply both sides of the equation by that reciprocal. Notice any number times its reciprocal cancels to 1. And that's how we get x by itself on one side of the equation. Now we can just put this in our calculators, and we can do it with a little bit more ease than simply dividing by negative 2/3. Both ways work. This way is just found to be a little bit more convenient for calculations. All right, let's look at a common misconception when you are moving quickly through solving equations and you're doing a really good job, and all of a sudden you're on a roll with the addition principle. Watch out for examples like this. Negative 3x equals 15. Often people see that negative 3 and they're like, oh yeah, here, I'm going to go for it. Plus 3 on both sides. But you guys can see that that's obviously wrong, right? Because first off, these guys don't even cancel. But if you left your answer as x equals 18, this is the importance of checking it. 18 times 3 certainly does not equal 15. So we got to be careful of these guys. And I want to make sure I erase that because, well, I don't want you guys to make that mistake. So let me just go ahead and try to get my stylus to work properly here. There we go. All right, now that it is, when you see something like this, negative 3 times x equals 15. What I want you to do is think about what's happening to that x. Negative 3 is being multiplied to it. So what undoes that? By dividing by negative 3 on both sides of that equation. And see you bye. There goes that negative 3. Leaving us, in this case, with an answer of x equals negative 5. And negative 3 times negative 5 does, in fact, give us a positive 15. All right, now what we really want to get to is solving multiple different types of equations that involve both principles, the addition and the multiplication principle in combination. Here's the first order of operations. Step one. Anytime you have parentheses, the first thing you want to do is distribute. If you don't have them, you can skip this step. Once you distribute, or even if you don't need to distribute, now you want to look for like terms on either side of the equation and combine those before you start moving pieces around. It's kind of like moving out of your house. You wouldn't get a U-Haul truck and move every single spoon and fork in there. No, you combine your like terms. You throw all your silverware in a box that says kitchen, and that's what would get hauled into that truck. Same thing here. Once we go ahead and distribute, and if we can, and combine our like terms, now what we want to do is use the addition principle first. We want to move all of the variable terms to one side of the equation and all the constant terms to the other. For our purposes here, in ease and calculations, what we're going to do is we're basically going to focus on moving all the x terms or variable terms to the left and all the constant terms to the right. The last thing we would do is the multiplication principle. Since this is the toughest one, let's save it for last. That way, if we're left with an answer like 2x equals 5, we'll divide by that 2 to get that x or that variable completely alone on that side of the equation. If you use the multiplication principle first, you're not necessarily wrong, but you could potentially be making more work for yourself. All right, now, if we look at example 1, there's really only one efficient way to go about it. And in this case, since 2y minus 3 equals 11, since we're looking at this, notice that nothing needs to be combined, and we can jump right to the addition principle. Let's get our constant term over to the right-hand side, leaving us with 2y equals 14. Now let's use that multiplication principle last. And since 2 is multiplied to the y, let's divide both sides by 2 to get that y completely by itself. All right, so pretty straightforward. Example 2, however, everybody could go about this one a very different way and still get the same results. It's kind of like your first move is flexible, and after that you're kind of locked into position, and you can only go about it one efficient way. Notice in this case, I could move the negative 3x to the left by adding it. I could move the 7 to the right by subtracting it from both sides. I could move negative 49 to the left and move the 5x to the right. You have lots of options here. So any way that you feel is most efficient, that's what you go with. Here, what I'm going to do is follow the same methodology. Since I want to bring all the x terms to the right, I've got a negative 3x, which means this 3x is being subtracted. What undoes subtraction? Addition. So we are going to add 3x to both sides of the equation. Now let's combine like terms. 5x plus 3x equals 8x, remaining us with an equation of 8x plus 7 equals negative 49. We've canceled our 3x on the right-hand side of the equation. Now last step, we want to get this 7 over to the other side. Since it's added, let's undo that addition through subtraction. And let's subtract 7 from both sides of the equation. Cancels on the left and moves that 7 over to the right, leaving us with 8x equals negative 49 minus 7, or negative 56. Now let's divide by that 8 to get x completely by itself. And that leaves us with an answer of x equals negative 7. If you're going to check this, don't go back here, don't go back here, don't go back here. You could have made mistakes. Instead, you always want to check with the original equation that was given to you. And if we do, let's plug in x equals negative 7 everywhere we see that value for x. So 5 times negative 7 plus 7 gives us negative 28. Negative 3 times negative 7 minus 49 gives us negative 28. That's how we know our solution is good, because both sides balance given that value for x. All right, now if you notice in example 5 and 6, we're going to work through some of these problems. And then the next part of this online lecture is going to be really rearranging formulas and solving some as well. So if you want to pause your video, you can, and you can work through these different examples and then come back and see how you did. Okay, I think we're ready to take a look at the results. Starting with 1, since 7 is subtracted from A, we want to get that 7 over to the other side of the equation. Negative 3 plus 7 is positive 4, so A equals 4. Looking at the next example, negative 6 equals negative 6x equals 42. This negative 6 is being multiplied to the x, so we're going to undo that by dividing both sides by negative 6, leaving us with x equals negative 7. Now this one, if we look at number 3, notice no distributive property, no combining like terms, but we do want to start with the addition principle first. And let's get those constant terms over to the right-hand side of the equation. And I'm just going to bring this over here. That leaves us with 2x equals 22. And in this case, we'll divide both sides by 2 now using the multiplication principle. And those 2's cancel, leaving us with x equals a positive 11. Hopefully so far so good. All right, let's see if I can erase this stuff. And we can now work on the next example, making a little bit of space for that. All right, now here, I'm going to write it over here just so we have space. 3c plus 13 equals negative 47. So looking at both sides of that equation, I want to get that c by itself and keep it on the left. So I'm going to undo the fact that 13 was added to both sides of the equation. So we're left with 3c equals negative 47 minus 13. This is where I start to see those sign issues, so just make sure you're validating your results. And if you do, you're going to get negative 60. Now, since we want c, not 3c, we'll divide both sides by 3 so we can get c completely by itself. And that leaves us with c equals negative 20. And if we go back and check this, 3 times negative 20 plus 13 gives us negative 60 plus 13, which equals negative 47. Oh, good. We didn't make any mistakes here. So we're on a roll. Okay, moving on to the next example. All right, it's funny. Number 1 trips up a lot of people, and I can understand why. Notice, if you have A, you can always sneak in that coefficient of 1. 2A is the same thing as 1A. So now let's go for it. Let's bring our constant terms to the right. And if you do 2 steps in one shot, awesome. I'm not going to, just because I'm trying to show every little possible step here. Notice what we're left with is 2A is equal to 1A, because we're only combining the constant terms, plus 8. So 2A equals 1A plus 8. We're almost there. So now 2A equals 1A plus 8. Now we're trying to get those A terms to the left-hand side of the equation. So what we're going to do is let's subtract that 1A. That's the same thing as just subtracting A. 2A minus A, you can see here is the same thing as 2A minus 1A, or just 1A. We're left with 1. We tend to write that as A as opposed to 1A. And in this case, we can see that A equals 8. You check that really quick. 2 times 8 minus 7 gives you 16 minus 7, which is 9, and 8 plus 1 equals 9 as well. So it looks good. Okay, first thing in number 2, we have to distribute that negative 3, which gives us negative 3y minus 12 equals 30. All right, now we can work with this because of the fact that, well, we no longer have parentheses. So I'm going to add 12 to both sides since it's being subtracted. That'll bring it over to the right-hand side of the equation. And you'll notice that leaves us with negative 3y equals 42. Last step, let's divide by negative 3. Make sure you're not adding because that negative 3 is being multiplied to y. We're left with y equals negative 42 over, or excuse me, my apologies, 42 over negative 3, which results in an answer of negative 14. Nice. And if we check that real quick, negative 3 times negative 14 plus 4, that gives us the same thing as negative 3 times negative 10, which happens to be 30. So we're happy. We've gotten what we're looking for, 30. All right, let's make a little room for this last one. Just going to clean this up a bit. Hate to see that smiley face go. All right, now that we've got some space here, some workspace, let's go for it. So first step, distribute 5x minus 10. Took this guy, distribute that 5 to both terms inside. Now let's write everything we've got. 5x minus 10 minus 3x equals 4x minus 10. Next step, what should we do? We're going to combine, and 5x minus 3x equals 2x minus 10 equals 4x minus 10. This one's going to look a little strange for a moment, but I'll make sure it makes sense as to why we get the solution we do. So we've got 2x minus 10 equals 4x minus 10. Now, when we're working with this, let's just follow the same suit. We want to get the number terms over to the side. And this is where things look a little strange here. If you take a look at this guy, whoops, excuse me, guys. There we go. Like I said, the stylus is a little finicky. If we add that 10 to the other side of the equation, notice both of these cancel. Guys, see that? You lose both of these. And what we're left with is 2x equals 4x. And that's where people get really uncomfortable and say, well, there's no solution. 2x can't equal 4x. But if you think about it, what number can you multiply by anything and it remains the same? That would be 0. So we can say at this point that x equals 0, or we can keep working it through. If we bring the variable terms over to the left-hand side of this equation, notice we end up with, on this side, 0. And 2x minus 4x is negative 2x. So negative 2x equals 0. Last step, we're going to have to divide by that negative 2. And 0 divided by any non-zero number is 0. So here, the only solution we get is 0. And that can cause a little bit of a discomfort because a lot of people want to say no solution. But that's not necessarily the case because x equals 0, that's a value. That's the only solution that satisfies this result. So here we don't want to say no solution. We want to say x equals 0. And you can check that if you don't believe me. You will see it's true. Both sides will balance. You'll be left with negative 10 equals negative 10. All right, I think we're ready to move on. And now the last thing we're going to do is work with formulas. When we're working with formulas, we're not necessarily just solving for a given variable. Instead, what we're going to focus on quite a bit here is rearranging our formulas so that they're more accommodating to our needs. Basically, if I had to solve for Celsius given Fahrenheit, this formula is going to become a pain in the butt after a while if we've got to do a lot of conversions. However, if we can rewrite this equation in terms of Fahrenheit, notice now we can just plug in our Fahrenheit value and solve for Celsius correctly every time. So our idea here is to rearrange these formulas so that we make them more efficient to use based on what we're trying to solve for. So let's go back a second here. And what I want you guys to start to get comfortable with is that formulas, well, first off, they might not necessarily always look the same. So you may solve a formula and it looks a little different than your peers. However, if you plug in your variable values, you get the same answers. That's okay. It depends on how you went about solving the formula. And there's no magic ingredients here. There's no magic recipe to solving formulas. Everyone's going to be a little different based on what's in front of you. In this case, we have f equals 1.8 c plus 32. And what I want to do is get c by itself. So what I'm going to do is not really focus on solving for c as a value, but basically getting c alone on one side of the equation. I'm not going to solve for it because there's two variables in this equation. You can't solve using one equation with two unknowns. Here we're just trying to rearrange it. So I'm still going to use that addition principle first in this case because it's easier than dividing everything by 1.8, I feel. So notice I'm going to get that 32 over to the other side. And what that leaves us with is f minus 32 is equal to 1.8c. Now the last step, notice I can't combine these guys. This doesn't become negative 31f. They're not like terms. Next step, I want to get that c completely by itself, so I'm going to divide both sides by 1.8. And there's our answer. C equals f minus 32 over 1.8. Now we can go the other way. If we started with this formula and we wanted to rewrite this to solve for Fahrenheit in terms of Celsius, now notice what we can do here. Since you have f minus 32 divided by 1.8 equals c, can't really do anything until we bring that 1.8 over to the other side of the equation. So what I'm going to do here is multiply both sides by 1.8. Notice that entire left-hand side of the equation is being multiplied to it, not just f. So these guys cancel. And here I've got f minus 32 equals c times 1.8. We usually write that as 1.8c. Now the last step to get f completely by itself is to, we'll go back here now, is to add 32 to both sides to get rid of the fact that 32 is being subtracted from f. Notice what will happen is these guys will cancel on the left, and we'll be left with f equals 1.8c plus 32. All right, so let's take a look at our next example. Getting close to an hour here on the video, and hopefully you're watching this in parts. But if this does exit out after an hour, just look for an added video to follow. But I think this recorder should make it past an hour. This is the first time I've had it go this far. All right, so let's look at another one. And I'll tell you what, we're going to be working with this quite a bit as well. These are advanced IV calculations. And this is the IV flow rate problem. And this problem is really important to determining how fast an IV is dripping. Basically, how many drops are dripping from that IV in 1 minute. So the formula is V over T times C equals R, which means volume divided by time, so volume of liquid to be infused in the body, divided by infusion time, times drop factor equals your flow rate. The drop factor, which is indicated in drops per milliliter, you would actually get that off of your tubing set. That's actually part of your on-hand supply. So that would be something that would be given to us, like when we solve dosage calculations problems. We know the on-hand strength of the drug based on the label. We can figure out how much to administer. Same idea here. So often what we want to know is what is the infusion time if we have a certain amount of volume to be infused, we know what set we're working with, and we know how fast that IV is dripping, how long will it take to infuse that amount into the body? Well, okay, looks like we made it past an hour, so I think we'll be in good shape here. So we can keep going. All right, so V over T times C equals R. We want to get T by itself. First thing we're going to need to do is get T out of that denominator. So let's multiply both sides by T. Notice it cancels T on the left. And we traditionally come back to the same equation, VC equals RT. Next step, we are looking for T, so now since R is multiplied to it, we're going to divide both sides by R. And there it is, T equals VC over R. All right, now let's solve for infusion volume. What if we know the infusion time, we know what we're working with, we obviously know the IV tubing set that's involved, and we also know the flow rate. How much volume has infused into the body after an hour, 2 hours, or a certain time interval? You may need to know that. So going back to our equation again, V over T times C equals R. Let's multiply both sides by T, because if we've got something in the denominator, if you've noticed, easier to just get it out of there to keep working. Leaving us with VC equals RT. Last step, get V by itself, so let's divide both sides by C. Notice whether the numbers are variables, they follow the same rules. So you're doing the same thing, you just might not be moving a 3, you might be moving a C instead. So what we're left with is volume equals RT over C. I said that because working with variables, let's say for instance a formula that contains completely variables, come on little eraser, and no numbers, it can be a little overwhelming, but notice that they represent numerical quantities, so they follow the same rules of the addition and multiplication principle as our traditional numbers do. All right, so if we look in this problem here, now let's choose the right formula to solve the job. An IV containing heparin and 250 milliliters of normal saline is infusing at 40 drops per minute. The infusion set is a micro drip set, which means really, really small drips, very precise. So that's about 60 drops per milliliter. That's how small those things are. Typical macro drip sets are 10, 15, or 20 drops per milliliter. So this is much, much smaller drop. Hence, it'd take a lot more of them to make up a milliliter of volume. In this case, we want to know the infusion time T. Notice 250 milliliters, that's our volume. 40 drops per minute. Careful, drops per minute is the rate, and drops per milliliter is your infusion set. They use C because they say, oh, that's what the tool's been calibrated to. That's basically how it's designed. So T equals, if we go back to this original formula, VC over R. So 250 milliliters times our drop factor of 60 drops per milliliter divided by R, our IV flow rate of 40 drops per minute, is going to leave us with what? What do we get as a result here? And if we do the math here, what we'll notice is this is going to work out to be 375 minutes. In this case, this works out to being 375. And you can see your units cancel, milliliters over milliliters, drops over drops. That's how you know you're in minutes. 375 minutes, well, 360 minutes and 6 hours. So this is about 6 hours and 15 minutes. That's how long it's going to take for 250 milliliters of the normal saline to infuse in the body based on these constraints. All right, let's do something a little bit different here. Remember, this is pretty much the traditional formula, at least what I learned in elementary school, was 9/5, not 1.8. And it's fun to do this one, or my version of fun. because here we're going to work with some fractions. So we want to get Celsius by itself. So the first thing that we're going to do is look at this example and think about, all right, if there's anything added to the side of the equation where Celsius is, let's get it over to the other side, and we can do so with subtraction. All right, and what that leaves us with now, I'm just going to bring it right over here, f minus 32 equals 9/5 c. Now, if you remember, when we have a fraction multiplied to the variable, we can undo that or bring that over to the other side by multiplying by the reciprocal. So I'm going to steal the space for this problem to finish off this Fahrenheit problem. So I've got f minus 32 equals 9/5 c. So what's the reciprocal? It's 5/9. Big mistake made here quite often, and this is what I want you to watch out for. We are multiplying this entire left-hand side by that reciprocal of 5/9. Notice these guys cancel, leaving us with c. So c doesn't equal 5/9 f minus 32. It equals 5/9 times the difference between f and 32. So let's just write that out. C equals 5/9 f minus 32. All right, now let's take a look at the rest of the stuff we've got here. Let's take a look at this business application. And just a few more before you practice and before we hit the end of this algebra video. So here's a nice business application. Anytime you look at the cost of producing a good, it's made up of two things: variable costs and fixed costs. And variable costs really depend on the number of units produced or sold, and fixed costs are the same whether you make 10 or 10 million of something. Like, for instance, the taxes on a space you might be utilizing to produce these goods. So in this case, we have a local surgical tool manufacturer who produces hemostatic forceps used to control blood flow during surgery. The company spent $1,100,000 to produce forceps in 2014. If it cost $850 to make each set of forceps, and the company paid $250,000 in fixed costs, how many sets of forceps were produced by this company in 2014? So just take a moment to think about that. All right, so let's take a look. Let's think about what we've got. The company spent this much, which means that's the total cost, $1,100,000, is equal to the variable cost times X. Well, $850 per forcep. So that would be our variable cost because it depends on the number of forceps sold. Lastly, their fixed costs are mounted in about $250,000. So now what can we do to get that X by itself? Let's subtract 250,000 from both sides of the equation. And when we do so, we are left with $850,000. Whoops, excuse me, guys. 850,000 equals 8.50x. So last step, what are we going to do? We're going to divide both sides by $8.50. And in doing so, we're going to see that this company produced 100,000 forceps in 2014, or I should say 100,000 sets of forceps in 2014. All right, moving on. Now, the next example that we have here is a traditional example, and we've seen it before. It's the BMI formula. BMI stands for body mass index, which is basically a percentage of body fat in the body. And that can be estimated by understanding a patient's weight and height. So in this example, let's make life a little easier. Let's say that BMI is equal to weight divided by height squared times 703. Now we want to solve for that weight. So if we look at this example, we're trying to get weight by itself. Well, first thing, this 703 is being multiplied to everything on the right. So let's divide by it on both sides to get it over to the left-hand side of the equation. And now what we're left with is BMI over 703 is equal to weight divided by our height squared. Since height squared is divided into the weight, what undoes division? Multiplication. So we're going to multiply both sides of this equation by height squared. And notice now we have what we're looking for. Weight equals height squared times BMI over 703. So let's figure this out. Well, first off, in this problem we're given, notice we're trying to figure out the man's weight based on height and BMI. What do we have to do to the height first, though? First thing we have to do is turn this into inches. 5 feet 9 inches is the same thing as 69 inches. So now let's set up our formula. Weight equals height squared, so that's going to be the 69 inches squared, times our BMI, which in this case is 26.4, and because we're working in the US customary system, we're going to divide by 703. If we were metric, we wouldn't be doing that. We would be using kilograms and centimeters. So in this case, the weight that we get when we do this in the calculator is approximately 179 pounds. Notice that we can substitute our data in. 26.4 is equal to weight divided by 69 squared times 703. We can plug that stuff in first and then rearrange our variables, or excuse me, our given values to solve for the variable we're looking for, which is weight. Either way, we're going to get there. But if we have to do this over and over again, it's really a good idea to solve for weight and have what's known as a working formula that we derive from our original formula. All right, so now it's time to put it all together, guys. This is our last part of the process. And what we're going to do here is simply just work through these different examples. And I want you guys to give it a try and then come back to this slide in just a moment. So if you'd like to pause and work through, let's see what you get for answers. All right, go for it. All right, so let's take a look at what these results will be. And if you guys can, oops, excuse me, we want to keep those annotations. If you guys can bear with me, what I'm going to do here is add a new slide so we have a little bit more room to play with here. And let's go ahead and work out these values. So starting with the current slide here, we're going to look at number 1. So in number 1, we have -3 times x minus 4 equals 2x minus 6. So first question, is this an equation or a formula? Since it contains only one variable, it's most likely just an equation, and we're just trying to solve for the unknown value for x. So step 1, let's distribute. And then we look to see if we can combine. But we can't. We have a constant and a variable term on each side of the equation. So let's go ahead and get those constant terms to the right, being very careful of signs so that you don't have to repeat this process. -3x equals 2x, in this case, let's see, minus 18. Now let's get those variable terms to the left, and we only have one. It's positive, so we're going to subtract it from both sides to remove it. And there it goes. So we're left with negative 5x equals negative 18. And you guys are fine with leaving decimal answers as your result. And I'm going to do the same. If we divide both sides by negative 5, we are left with x equals a positive 3.6. And you can check your answer by substituting it back into that original equation. And I'll let you try that, and you will see that both sides will balance. So that's our first result. In this case, whoops, sorry about that, guys, x equals 3.6. All right, so let's now look at the next one. And the next one's interesting because while we've solved proportions many, many times before, we've never really looked at one quite like this. And honestly, it's something that you can do with cross multiply and divide or using the cross products. I'm going to use cross products because I think that's a nice way to generalize solving this problem. So what we've got here is a plus 6 over 5 equals 3 over 8. And we know that whenever we have a proportion, two fractions being equal, we can use their cross products to solve. So notice 3 times 5 is going to be equal to, and this is where it's different than what we've seen before. I'm going to put that 8 on the outside left, 8 times a plus 6. Notice the entire expression a plus 6 is being multiplied to 8. Now we can go for it. 15 equals 8a plus 48. Now, because a is already on the right, I'm not going to move that over to the left like I have traditionally in other problems. Instead, what I'm going to do is get a by itself by removing this constant term and bringing this actually over to the left-hand side of the equation to get it out of there. And 15 minus 48, that gives us what we get here. We're going to get negative 33. So negative 33 equals 8a. And our last step is let's divide both sides by 8 to get a completely by itself. And when we do so, if you plug this into the calculator, you'll see that a equals negative 4.125 or negative 4 1/8. If you're going to leave an answer, try to leave it as a mixed number or a decimal, not an improper fraction, because we could measure, let me try that again. We could measure this quantity very easily when it's expressed in that manner. All right, so our answer here is a equals negative 4.125. Almost there, guys, almost done with this complete series. We've just got a few more to go. All right, so let's go ahead and see if my eraser wants to work. And it does, that's a good thing. Let's go ahead and take a look at our last few examples. All right. Okay, so now we have 3x, oops, a little messy there. We have 3x plus 2y, my stylus is tired, equals 16. Now this is not an equation, this is a formula. It contains two variables. All we're trying to do is rearrange this formula so we can talk about y. So what we want to do is we want to get not just 2y, but we want to get y by itself on one side of the equation. So since this 3x is added, let's go ahead and subtract it from both sides of the equation. And that leaves us with 2y equals 16 minus 3x. Now the last step, let's divide each term by 2, or each side of the equation by 2. So you can leave your answer like this, 16 minus 3x over 2. I'm a little bit more particular. I like to separate these terms to see what we're actually left with. And that's also because this is a special type of equation. It is a linear equation, and we can get the y-intercept and slope when we look at the individual terms, not one expression. So this is okay, but this takes us a little further, and this is better. In fact, this is much better if we have a negative in that denominator. So there's our final answer. Y in this case equals 8 minus 3/2 x. All right, getting there, guys. 2 more to go. Y equals 8 minus 3/2 x. All right. Let's clean this up. My goodness, thank goodness for technology. This makes things very easy. All right, so the next one we've got number 4. A equals VF minus VI over T. This is a very common formula used in physics, and this is how we determine acceleration or average acceleration by determining the change in velocity, v, over time t. So in this case, we have a formula, and we want to know, all right, well, let's say we know some of these pieces, and what we really want to figure out is, based on how fast an object is accelerating, what would be its final velocity given the other values known? So notice in this case, what we want to do is first multiply both sides by t, because we want to get that t out of the denominator. And instead of writing TA, what you'll mostly see, because this stuff is often written in alphabetical order, is AT. So we removed it from the right-hand side, keeping in mind that we multiplied this entire right-hand side by t. And we're left with AT equals VF minus VI. All right, last step to get VF completely by itself, since VI is subtracted, let's add that VI, that initial velocity, to both sides of the equation. And there it is. VF is equal to AT plus VI, or VI plus AT. Doesn't really matter how you write it, but this is what you would see traditionally in a physics class. All right, we're almost there. VF equals VI plus AT. Last one. We're going Fahrenheit to Celsius. Let's rearrange this formula so that it can solve for, in this case, Fahrenheit given Celsius. Come on, little stylus, one more to go. Gonna make it. All right. Okay. So last one, number 5. Here, we're looking at the Fahrenheit to Celsius formula, which says Celsius is 5/9, the Fahrenheit measurement, minus 32. So this one's a little different than the others that we've seen because we have this 5/9 outside of the equation. So, or I should say outside the expression on the right-hand side of the equation. So I'm going to make life easier, and we could distribute, or let's get that 9/5 over to the other side of the equation, just to make life a little easier. Let's multiply by the reciprocal so we can cancel this guy. And that leaves us with 9/5 C equals F minus 32. All right, we're trying to get F by itself. So last step, let's add 32 to both sides. Was not so bad. If you distribute, it's just going to take a little bit longer, but you'll get there and you'll have the right equation. It just may look a little different than this. In fact, I should say you'll have the correct formula. So F equals 9/5 C plus 32. Okay, we've done it. We've covered all of it. Now, this should help you with your solving equations and solving formulas worksheet. If you guys have any questions, you can certainly reach out to me via email. You can also stop by the math lab or stop by to see me during office hours. If you're working through problems on the homework worksheet, know that there are solutions on the back so you can check your work as you go along. And if something doesn't seem to measure up, just go ahead and take a picture and email it to me so I can give you some feedback. Please do let me know if you have any questions, and I hope you found this to be helpful. Thank you.